Hello students, in lecture 6 of advanced calculus, here we shall discuss the mean value theorem, total concept of total differentiability, about the composite functions, and the sufficient condition for the continuity of a function of two variables. So first we see the statement of mean value theorem for the function of single variable. The statement is like this. If we have two real numbers, suppose a and b, and where a is less than b, suppose we define a function f from interval ab to the set of real numbers. If this function is continuous on interval ab and differentiable on open interval ab, then there exists a number c in the open interval ab such that this value fb minus fa equal to f dash c into b minus a. In other words, that there is some point c in the open interval ab, so derivative of that function f at c is equal to fb minus fa divided by b minus c. So geometrically we can look at the situation in this manner. Suppose we have this function y equal to f of x, and there are two real numbers a and b, and you are also given that a is less than b, so definitely a will be on the left hand side. Now if we extend this a here, then it will intersect this curve y equal to fx at this point, and then the coordinate of this point will be a, and at a value of y will be f of a. So the coordinate of this point are a, f of a. The x coordinate is a and y coordinate becomes f of a. Similarly here this also becomes b and f of b. Now what will be the meaning of fb minus fa divided by b minus a? So suppose I draw this line parallel to x-axis, and at this angle subtended by this line joining the points P and Q, then it becomes a right angle triangle if I consider it as L, this point as L. So from this triangle PQL, tan theta will be equal to perpendicular divided by base. So you can easily see the length of base is b minus a. The length of base is b minus a, and the length of perpendicular is, because corresponding to this point the y coordinate is f of a, and corresponding to this point, if we look at the situation, we draw the perpendicular here, this is f of b. So I can say this length will be equal to length of this perpendicular QL, and this length is equal to fb minus fa. So clearly this fb minus fa divided by b minus a is the perpendicular over base, or perpendicular divided by base in this triangle, and that is equal to tan theta. So tan theta, you know, is the slope of this line PQ, slope of this line PQ. So here we can say the slope of this line is given by fb minus fa divided by b minus a. Similarly, if we have this point here, then this corresponding to this point, the value of x is c, then this point c is lying between the numbers a and b. So we can say this c lies in the interval, open interval ab, and if we say f dash c, if f dash c means the slope of tangent to this curve at point C. Slope of the tangent to curve at this point C. If this is also theta, then you can say this f dash C equal to fb minus fa b minus a. So the mean value theorem actually, what is the geometrical meaning here in the mean value theorem? That if you are given a function f from the closed interval ab to r, which is continuous in the closed interval and differentiable in the open interval, then there exists some point C at which the tangent to the slope, or I can say the slope of tangent to the curve will be equal to the slope of the line joining the points P and Q of this curve. So this is the meaning of mean value theorem here, geometrical meaning. So the same theorem in case of two variables we can extend. In that case we can write the statement as here. If fx means partial derivative of f with respect to x exists throughout the neighborhood of a point AB, and fy AB means partial derivative of f with respect to y also exists at the point AB, then at any point a plus h b plus k of this neighborhood, the value of f of a plus h b plus k minus f of ab will be equal to h fx a plus theta h b plus k into fy of ab plus eta, where theta lies between 0 and 1 and eta is a function of k tending to 0 with k. So you can remember this statement of mean value theorem in case of two variables. So how this theorem can be established here? You see, if we write f of a plus h minus f of a plus h b plus k minus f of ab, then if we subtract this quantity and add the same quantity, then it makes no difference here. Since according to the statement given here, fx exists in the neighborhood of the point AB, therefore by the Lagrange's mean value theorem, since fx exists, that means you should keep y as constant. So here let us look at this one, and this part corresponds to the first two terms in equation 1. So here you can see the y coordinate is same in both the situations, so that means you are varying the x coordinate only. So here f of a plus h b plus k minus ab can be written as h fx a plus theta h b plus k, where theta lies between 0 and 1. Actually this equation 2 here is equivalent to this part, is equivalent to this equation here. How this is equivalent to that? Now it becomes the case of single variable. Now it becomes the function of single variable because here we are keeping y coordinate as constant. So just look at this function as a function of single variable. So if you compare with the earlier case, for you this part corresponds to b and this part corresponds to a. So you can see fb minus fa is equal to, here in place of f dash, we are having fx means partial derivative of f with respect to x, and obviously this b plus k is constant, so in place of c, this quantity is here. In the case of single variable, we have already mentioned that c is a number lying in this interval a to b. So for that case, your C must belong to the interval a to a plus h. So that is why this C is lying between a to a plus h, because here you have considered theta in such a manner that theta lies between 0 and 1. If you take it as 0, then it becomes a only, but a is exclusive. We cannot include a here in the open interval. So that is why we are keeping theta greater than 1. So obviously when you take theta greater than 0, so it will be right of a to a plus h interval is like that. Then if you are taking theta greater than 0, so the point will be somewhere right to this. And when you take theta equal to 1, it will be a plus h. A plus h means the point will be here, but it cannot be included. So that is why we are keeping theta less than 1. So if you take theta less than 1, the point a plus theta h will be in this interval a to a plus h. So this equation 2 completely analogous to this statement here. And this for b minus a means the difference of these two. So here, as I have already mentioned, b means a plus h. In this situation, b means a plus h and a means a. If you take the difference, you get h here. So this equation 2 is completely analogous to the mean value theorem of the single variable. Also, fy exists, that is given in the statement. Fy exists at point AB. So by definition, you write like this. Note one more thing here. Fyab is equal to limit of this thing given in the left hand side. Now if I take the difference of these two, that is equal to 0. And if I remove the limit here, then the difference of this quantity minus, I can say this quantity minus this quantity is not equal to 0, but nearly equal to 0. So here we can say that this difference f of a and b plus k minus f of ab divided by k minus fyab is equal to some very small number eta. Let this number eta is here, and if we simplify this equation, we get this equation. So here eta is a function of k, and it tends to 0 and k tends to 0, because when k tends to 0, that becomes 0, and we get the situation like this here in this equation. So this equation can also be written like this. Now you substitute the value of this quantity and value of this quantity here in equation number 1. We get the desired result. This one means this is the statement of mean value theorem for a function of two variables. Now theorem of total differentials. So what is the meaning of total differential? We will be able to explain with the help of this theorem. Suppose we have a function of two variables f of x, y, and we are denoting it by z. Means z is equal to f of x, y. This notation is written here in such a sense that when you take image of x, y under f, that is equal to z. Otherwise, you can simply say that we are taking that z is a function of two variables x and y. Now let xy and x plus delta x, y plus delta y be 2 points, so that delta x and delta y are changes in the independent variables x and y. And let delta z is be the consequent change in the dependent variable z. So we can have z plus delta z equal to this quantity x plus delta x, y plus delta y. From 1 and 2 means if we subtract equation number 1 from equation number 2, we get delta z in left hand side, and in right hand side we get this minus this. So again, as we have done in case of the proof of mean value theorem. If we subtract this quantity and thus add the same quantity, we get this expression as here in equation number 3. Here we change delta z. The change delta z has been expressed as sum of two differences, to each of which we apply Lagrange's mean value theorem. So for this, because in this case we can say we are keeping this as fixed and we are changing y, and in the second case we are changing x and we are keeping y. So these two parts independently can be considered as the case for the mean value theorem of single variable. So accordingly, if we modify equation 3 in view of Lagrange's mean value theorem, first part can give us this expression where theta 1 lies between 0 and 1. We write this f of y, x plus delta x, y delta 1, y theta 1 delta y minus fy xy epsilon 2. So epsilon 2 depends on delta x and delta y. So here we are applying the same logic. We are applying here same logic as we have done in case of the Lagrange's mean value theorem, as we have written this equation in this form. So exactly according to the same logic, here in place of eta, here we write epsilon 2, and it will be tending to 0. It will be tending to 0 when delta y tends to 0, fy tends to 0. So again, considering the case, the second equation, second difference, we get this quantity. Obviously this theta 2 will be between 0 and 1, and here theta 1 is also between 0 and 1, and let this is epsilon 1. Epsilon 1 tends to 0 as delta x tends to 0. So using these two equations here, using equation number 4 and 5 in equation number 3, so 3 can be written as delta z equal to delta x, fx, f subscript x, y, delta y, fy xy, epsilon 1 delta x plus epsilon 2 delta, in fact it should be delta y, epsilon with this thing. So here are two parts. This fx means curly z by curly x delta x. This means curly z over curly y delta y, and this epsilon 1 delta x, epsilon 2 delta y. There are two parts. The first part here is called the principal part. Thus the change delta z in z consists of two parts as marked in the last slide. The first part is called the differential of z, and it is denoted by dz. If we take z equal to x in this equation, so you can have dz becomes dx, and here it becomes curly x by curly x delta x, and here curly x over curly y, but partial derivative of x with respect to y will be 0. So this part is 0 and this is 1, so we can write dx equal to delta x. So in place of delta x you can write dx, and similarly in place of delta y we can write dy. So dz becomes this quantity. So in this equation here, delta z equal to this first part gives you the total, gives the differential of function z, and that is given by this equation dz equal to this thing. It should be carefully noted that differentials dx dy of independent variables x and y are the actual changes delta x and delta y, but differential dz of dependent variable z is not the same as the change delta z. It is being the principal part of the increment delta z. So now we talk about the composite functions. What is the meaning of composite function? Suppose you are given that z is a function of two variables x and y, and x is further a function of variable t and y is further a function of variable t. That means x, y are themselves functions of third variable t, In that situation, z is said to be the composite function of t. We can visualize the situation like this. If z is the dependent variable, depending on two variables x and y further depending on the variable t, and you want to find the derivative of z with respect to t. Basically here z is composite function of t. Then the formula for dz by dt is will be like that. Dz by dt, we will proceed in this manner. Curly z by curly x into dx by dt plus curly z over curly y into dy by dt. So it is the formula for the derivative of this composite function. And this dz by dt is called the total differential coefficient or total derivative of z. And total differential of z is given by this formula, as we have already explained in the theorem of total differentials. Now look at another situation. If we have the function z of two variables x and y, you can write z as a function of x and y. That means z depending on x, depending on y. Further, x and y are functions of two variables r and s. Y is also function of variable r and s. Then how we find the total differential coefficient of this z? In that situation, this z is composite of two variables again. Further composite of two variables again. So here we will take the total derivative in the form of partial derivatives. For example, here curly z by curly r and curly z by curly s. If you find curly z by curly r, that will be equal to curly z by curly x by curly r plus curly z by curly y into curly y by curly r. Similarly, curly z by curly s is equal to curly z by curly x into curly x by curly s plus curly z over curly y into curly y by curly s. Just visualize the situation here. When we are taking with respect to r, we move like this along this right arrow, this red arrow here means you are finding curly z by curly r. Then you proceed like this, curly z by curly r equal to this into this along the red arrow plus along the red arrow curly z by curly y into curly z by into curly y by curly r. So this will give you curly z by curly r. You can find here curly z by curly r, and along the blue arrow you can find curly z by curly s. Curly z by curly s means that will be equal to, you proceed along this curly z by curly x along the blue arrow into curly x by curly s, and here curly z by curly y plus actually this will be this expression here, curly z by curly s. Along the blue arrow you can travel and you can add the terms. So this is the visualization here. Now let us discuss here the sufficient condition for the continuity of a function of two variables. As we have already explained in the earlier lecture that in case of a function of two variables, the existence of first order partial derivatives doesn't imply the continuity of the function at the same point. We have already discussed some illustrative examples where at a certain point the first order partial derivatives were existing, but the function was not continuous at that point. So there is a sufficient condition for the continuity of a function. I should keep in your mind this statement here. A sufficient condition that a function f be continuous at a point a, b, and of course this f is the function of two variables. A sufficient condition that a function f of two variables be continuous at point a, b is that one of the partial derivative, just keep in mind, one of the partial derivative exists and is bounded in a neighborhood of AB and other exists at the point AB. That means if two first order partial, both of the partial derivatives of first order must exist, and one of the partial derivative must be bounded in some neighborhood of this, then this is the sufficient condition for the continuity of function of two variables at a given point A. So you can keep in mind. And one corollary regarding the same, a sufficient condition that a function be continuous in a closed region is that both the partial derivative exist and are bounded throughout the region. So in a closed region, we require some stronger condition. In this case, both the partial derivatives must exist as well as both must be bounded in that closed region. So this is it about this lecture, and the content mainly have been taken from these two books. You can consult. Thank you.